Hey guys, what's going on? It's Danny, and today we're going to be talking about the concepts of recursion. We're going to start this, mini lesson video by walking through a solution to a problem like 509 Fibonacci number, and then we're going to dive into how to solve other problems using this same approach. So stick around for that. I guess the people who are most likely watching this video, you're either one or two people most likely. You're either someone who is learning about recursion just out of CSA, maybe in CSA and just want to learn more about recursion. So this video is for you. Leave any questions you have down below and any more questions you have or any more topics you'd like me to cover down below. Or you're maybe not a new person to coding. Maybe you're more an experienced developer. You know a lot about coding, and you're just watching this video to see, I guess, someone who's less experienced at coding and see their understanding of recursion. And if that's the case, I'd love for you to leave any feedback you have down below. Without further ado, let's get into the video. So recursion is basically a concept of a function that will call itself. So it's kind of a self-looping function, very similar to dynamic programming, very, very similar, except instead of accessing earlier elements in earlier small sub-problems like in dynamic programming, you're actually just solving those sub-problems on your own each time. And this can actually lead to some complexity issues. Sometimes it's not very optimal, but a lot of the time it makes code very readable, very simple, and it can also be confusing though. And so the first thing I want to do is I want to talk about Fibonacci number. And so to read the problem, I guess if you haven't attempted this problem on your own, I try it right now. This is a great problem to learn about recursion, and a great first problem for recursion. We used this today in my computer science club, and everyone seemed to enjoy it and got the hang of recursion pretty fast. So to start off by reading the problem, the Fibonacci numbers, commonly denoted as f of n, form a sequence called the Fibonacci sequence, such that each number is the sum of the two preceding ones, starting from 0 and 1, that is. And that can sound confusing, but in reality, it's just a string of numbers that increases as so. It'll go 0, 0, 1, 1, 2, 3, 5, 8, 13, and a lot of you math coding people, you can look at this. If you don't know a Fibonacci sequence, looking at this, you can kind of understand the pattern yourself. I got 5 by adding 3 and 2, 8 by adding 5 and 3, and so on. And that's just the basic introduction of the Fibonacci sequence. It has so many ties to, I guess, the golden ratio and all these other mathematical concepts. So it's something that's worth learning about, but not the topic of this video. The topic of this video will be, though, how to find a number of the Fibonacci sequence given the step it's in, I guess. And so in order to solve a problem like this, I guess we're going to look at the solution first thing. So this is the solution of the equation, or to the, not equation. This is the solution to the problem. And it has two main components. It has the base level, the base check, and it has the, I guess, what it's running. And so whenever I start questions like this, I'll actually start with this down below one. And this is basically in order to find a number in the Fibonacci sequence, as denoted here. Right here it says to find f of n, it equals to f of n minus 1 plus f of n minus 2, as long as n is greater than 1. And so now we know our check. This one line tells us everything we need to know. The first part tells us that this is what we're going to be calling over and over. In order to find f of n, we need to run these two equations. So we're going to go return Fibonacci sequence of n minus 1 and plus n minus 2. And that's great. Now it's going to run both of those calls. But what's going to happen is, imagine we had a number like 10. It's going to go minus 2, minus 1, and it's going to keep subtracting smaller and smaller and eventually get negative. And so at a certain point, you need to stop your recursion calls, and that's called the base case or the base level. And that's where you want to stop in general. And that, in this case, is going to be n greater than 1. So over here we have, in our if statement, this is the stopping statement. Usually, if you're going to stop a recursive thing, it's going to be if some condition is met, then return a static value. Static as in you're not calling another method, you're just returning n. I guess static isn't a great word to use there. But aside from that, yeah, so we know n is greater than 1, so if n is less than or equal to 1, we're just going to return n. Because if n is 1, and it's the first number in the sequence, it's just going to return 1 because that's what it is. Or if it's 0, it's just going to return 0 because that's what the 0th number in the sequence is. See, f of 0 equals 0, f of 1 equals 1. So this gives us our base case and our recursion, and you'll see if we submit this, we get 25% complexity. And you may be looking at me saying, Danny, why do we have such, I guess, garbage complexity? And that's because there's so many faster ways to do this specific problem. There's a math way to do it. There's dynamic programming. There's for loop approaches. There's so many better, more optimal approaches to this, and this one just isn't the best. This has, I believe, O to the 2 to the O2, or big O of 2 to the power n complexity, which means it looks like this. It's O of 2, if I'm not saying that right. It looks like that, 2 to the power of n. So let's say you return 3, it's going to make 8 total calls on average, give or take. And that's just not something that you really want to be doing, and that's part of what's killing the complexity. All right, yeah, but overall, recursion isn't always the best, but if in this scenario specifically, if you were to be at a hackathon or some kind of, or a high school hackathon or some kind of coding competition, using a recursive solution for a problem like this is just perfect. This is exactly what you need to do. This took 3 lines. It could take 2 lines. It's just perfect. It's what you need. So while applying these concepts, we're going to go on to the next problem where we're actually going to solve it together. Oh, don't need that. We just call it power of 2. So if you haven't solved this problem, I'd recommend trying it on your own first. This is another very typical easy problem that I'd recommend trying just as a good start. And it goes as such. Given an integer n, return true if it is a power of 2. Otherwise, return false. An integer n is a power of 2 if there's an integer x such that n equals 2 to the power of x. So this is basically just saying, is the number given a power of 2? Yeah, so the way we're going to figure this out is we're going to think, how do we know something's a power of 2? What is something that's a power of 2? Let's think. So something that's a power of 2 would be 2 times 2 times 2 times 2 times 2 times 2, potentially forever. And what does this mean for us? This means that we can actually backtrack through this solution. Backtrack, also not great. We can go backwards through the solution, though, to find if it's a power of 2. Numbers that aren't going to be a power of 2 are going to be things that are odd, or things that just aren't, I guess, just aren't a power of 2. Right here, a great example is going to be the number 3. The number 3 is not made up of 2 times 2 times 2 times 2, and it's not a power of 2. And so the way we're going to solve this problem is we're going to think, what do we want to do? So is a power of 2, how can we shrink this into smaller problems? I'm thinking, if we have a number like 16 or 8 or 32, if we half that, if we divide by 2, we take away this last times 2, and then we check, is this the power of 2? And we keep going and going and going until eventually we get until we end up with nothing. And so the recursive call for this is power of 2 of n divided by 2. And so now this is going to check if half of the number is also a power of 2. Because if it's a power of 2, half of the number will also be a power of 2, because that's just half of it. That's just divided by 2 instead of times by 2. So once again, that's working backwards through this. For this, if it was this, we'd look at is power of 2, and then we would delete these last 2, and check these, and so on. And now we're going to return this, and I'm just going to run the code, see what happens. But it's really not going to do much, because you need more than just this one recursive thing. Remember, we need the base case. Now, what is the base case? What is the smallest possible number? Now, in problems like this where you're scaling, you're doing a lot of heavy math, usually the number is going to be a very significant number. So I'm not just going to jump right to it. It could be numbers like 2, 1, 0, less than 0. It could be any of those. So now we're going to think, what could it possibly be? So if it's 2, is 2 a power of 2? And that's yes. But if we divide by 2 again, we get 1. And 1 divided by 2 is 0. And 0 is not a power of 2. So I'm actually not too sure what exactly this problem wants. I think it is that looking for 1 is the end. It's not exactly too clear. But if it were to enter in the value of 0, of course, as a test case. But let's say it just goes down to 1. So if n equals 1, we're going to return true. This means that we divided by 2, we divided by 2, we divided by 2, and we finally got the answer, right? And this makes sense. You know, if it's 1, then we would just keep dividing and halving until we got that 1. And that means that it's even. But in reality, this doesn't work, as we'll see. It works for 2 cases, of course, because those are the cases where it works. But it doesn't work for number 3 because of integer division and the integer division operator in Java specifically. So in Java, when you divide integer by another integer, it actually performs integer division, where it concatenates the remainder. So in this example, it does 3 divided by 2, which is supposed to be 1.5, but it actually concatenates that. And it gets rid of the The last, or it truncates it, sorry. It truncates the 1.5 to just 1. And so we're left with 1, and that gets us to here, and we return true, which just doesn't make sense. So there's going to be more that's going to need to be done. We're going to need to consider, is the number also divisible by 2 before we do the call? So let's see, okay, I'm not going to turn to it. So if n mod 2 should equal 0 in every single case. If n mod 2 ever does not equal 0, we know it's false. So we're actually going to add this into our return statement, and this is what has the optimal complexity. There's better ways to approach, or simpler ways to approach this, I'd say, but the simplest is this. Actually, no, we'll start with the, I guess, simpler approach, and that's if n mod 2 equals 0, return false. And then I think there is a 0 base case that this is actually going to fail. So, here, wait, what? So, 16. So what this is checking is if, or actually, we're just going to go, we're not going to try to, I was trying to make it simpler for you guys, but I'm just going to go right to the proper solution. Is this uses the AND operator differently? Oh. Alright, yeah, so there we go. But yeah, so basically the reason why we have this n mod 2 in the first place, for at n equals 0. So n equals, if n equals 0, return false. So that's the extraneous solution that I was talking about earlier. Sometimes LeetCode problems, or problems in general, will have bounds on the outside that you need to account for that you can't always achieve, or you don't always exactly know. Usually if you're in an interview situation, you'd be able to ask, but in this we can't really ask. So now we're going to go back through the solution. We're going to say we know what this is, but why do we do the n mod 2 equals 0? And that's because at every single point, once again, at every single point, the number needs to be divisible by 2. If it's ever not divisible by 2, we know something's wrong. The only reason it can't be divisible by 2 is if it's 1, and that means it's true and it's perfect. But otherwise, it should be divisible by 2, and the half of it should also be divisible by 2. And this scales, but as you can see, the runtime of the complexity of this isn't amazing. It's 42%, which, or not 42%, sorry. Well, 1 millisecond is what really matters. Yeah, kind of. But that's because it's recursion. Recursion isn't that fast. There's simply better ways to do this using math approaches and just other various approaches. Like down here, it actually asks you to solve it without loops of recursion. But for this scenario, I feel like this is a somewhat straightforward problem that will help a lot of you guys out. And one of the biggest things to take away from recursion in general is that when you're writing these recursive, I guess, programs, it's a very different approach to regular solutions, I'd say. Because in regular solutions to different other problems, typically you'd have maybe some kind of loop that you're iterating through, and you're using some kind of data structure. But with recursion, it's really just, you're not using any complex data structures, you're not really going to be using any loops or anything. You're just going to be calling the same method over and over, and it can get confusing at times, like with the case of this, with the case of the 0, and a lot of the times when people struggle with this, it's because they can't come up with these outside solutions, like this n equals 0, this n equals 1, these base cases, and it can be tricky to think about handling these numbers. But I think that if you're someone new to programming, you're just at CSN and you're watching this video, trying these two problems, and maybe watching my next video I have coming out on, where is it? I'll pull it up real quick. Little sneak peek on pow x to the n. This is a great problem. This is a good problem I'll be covering in the next video. It's another great recursive problem, but once again, it's not very optimal to use recursion. But recursion makes these problems so simple and can be so applicable in all your coding competitions and just programming in general. So, yeah, that's just about the end of the video. If you learned anything new from this video, feel free to comment down below. If there's anything you think I missed in this video, or anything you think could use some clarification, feel free to comment that below too. I love hearing feedback from you guys. Yeah, that'll be it. See ya.